Hello and welcome to KAUST Live. We're coming to you from the Winter Enrichment Program. This year's theme is time.
4 or 5, and then, the city that you walk around has some buildings from, 1400, so, incredibly old, hundreds, thousands of years old. Right. And then you see these ancient ruins preserved, these crumbled down walls, or the pyramids of Giza from 5,000 before Christ. And you think, wow, it's incredible. And then as you go back, you get into bigger and bigger numbers. And, we think about the oldest human ancestor, 2 million years old. But if you think about the entire span of our planet in geological time, even 2 million years old is the last sliver of your thumbnail on the body of life, right? Wow. It's just unbelievably vast distances of age. 4.567 billion years is when our solar system formed and when the Earth and all the other planets formed. Actually, surprisingly quickly, as this cloud of gas and dust in the universe, in the Milky Way galaxy, started to condense by gravity and started to swirl and clump up. And the big part of it made the sun, which started to burn because of gravity. It actually ignites the hydrogen fuel. And outside, where it's colder, you get other little clumps, which are the planets.
Right.
And Earth is famously the third rock from the sun, right. Mars the fourth, and on and on. But we're part of a very big system that formed about 4.5 billion years ago.
Do we know how much older or younger any of the planets are from each other, particularly since we'll get into talking a little bit about Mars? Do we know in geologic time, are we older or younger than Mars in particular?
So we do, actually, and you might ask, how is that even possible? But it started out by actually finding samples of the Moon and Mars here on Earth as meteorites. And so the early history of the solar system was incredibly violent. There were collisions all the time between these developing bodies. And so Earth grew by this accretion of all these different collisions. But in that process, the other planets, like Mars and the Moon, also got smacked.
Right.
And as they got smacked, some of those fragments came out into space, circled around the sun, and then came into Earth and fell on places like the Saudi Arabian desert or in Antarctica, after traveling through space for billions of years. But we can then analyze the minerals and the chemical composition, and we find that they're really exactly the same age. Yeah. They have slightly different compositions because as the solar system disk formed, the energy from the sun blew wind out in different isotopes and compositions further and further out. So that's why we have the gas giants far out in the distance for Saturn and Uranus and Jupiter. Right. The sun blew all the gases out into the distant part of the solar system and left behind these rocky planets in the core with only a little bit of water, just enough on Earth to get life going.
Right. So the start of life is quite recent in geologic time, I suppose. Although it's put at 3.5 billion years or so, I think, or more. And so you've studied some of these oldest fossils. Talk about where you found them and what they are as organisms.
Yeah, so most people think about life as elephants and camels and the beautiful fish in the sea. Right. That all happened relatively recently in the last 500 million years of the Earth history. So if we think of 4.5 billion years, it's again, all the big life we see is not the fingernail, but maybe the thumb on the history of life if we think about the body being 4.5 billion years old. But yeah, I've been incredibly fortunate. I've studied some of the oldest life, very simple single-celled organisms that live as communities and actually end up building rock structures that you can see preserved in the geological record. And the oldest, most convincing evidence for life is at 3.5 in northwestern Australia, in the Pilbara, where I do most of my field work. And then a couple of years ago, we found traces of life, hints of really compelling life at 3.7. So we're pushing everything back, but then we essentially run out of the rock record at 3.8 billion years. Because that very early history of the Earth was so violent, any rocks that formed actually got smashed and vaporized and recycled into the mantle. And so we just don't have any record from about 3.8 billion years back to the formation of the planet. And that's when life started somehow.
Right.
And that's the mystery of that we actually can't see.
And I believe that you've toyed with the notion that maybe it didn't happen in the ocean or in the coast, but in the interior in steam vents and things. Talk a little bit about where we are in terms of where we think life started on the planet.
So, I mean, all of us are taught in schools that life evolved out of the oceans and came up to land, and, you know, we started as fishes and then evolved into animals and dinosaurs and then humans and stuff. But it turns out that there's a fundamental problem with life starting in the oceans. And this is something I'll talk about in the lecture today, is that, you know, in astrobiology, the field that I'm in is looking for signs of life elsewhere. A really common thought is to follow the water, because everywhere on Earth, life needs water to keep metabolizing. It's the fluid that makes things work. And in fact, water is very common across the solar system. It's in comets, it's on other planets. We know that there's evidence of water on Mars, for example. And so that's actually a quite common element. But to get life started, right? So if you have life, that's a really good exploration model. Follow where there's water and you can have it. But to get life, a really paradoxical thing is that in order to make simple molecules with carbon and oxygen, you get those very commonly in comets and meteorites. They're falling in on Earth all the time today. Organics are very common in the universe. But to make organics change from simple molecules to very complex molecules, which you and I use to breathe and make our DNA and everything, you actually need reactions that dry the system out. So if you think of a couple of building blocks, like bricks, right? And you try and put them together, if it's wet, they just dissolve and fall apart. But if it's dry, the energy of kicking out a water molecule, if they're slightly wet, actually makes those molecules stick together. You need drying conditions.
Interesting.
So that's why there's a really large shift in the community now from an origin of life in the deep sea around these hydrothermal vents where black smokers are coming, there's mineralized fluids, onto land. And there's a number of really strong benefits to that. Not just the fact that you can wet dry, you know, if you think of a geyser erupting, the water level changes, so it dries out and gets wet again, dries out. You're making polymers all the time. But hot springs are typically in these fields of more than 100 different pools. They all have different chemistry, they have different concentrations of elements necessary for life, and they can mix and match things. So, like in terms of a complexity factory, that is it. And we've gotten extremely excited about the potential of hot spring fields on an exposed land surface because of that theoretical body of knowledge, but also because the old rocks we work in, the 3.5 billion-year-old setting in the Pilbara, turns out the life was living in a hot spring environment.
So talk about that location and where you've been working, and what led you to start down this path of thinking that life may have started in these areas rather than the coast.
Yeah, it's actually a nice story of science. It's a very typical story of science. We started off in one direction and then took a complete U-turn and went in another direction just recently. These stromatolites had been found in the Pilbara back from about 1980. It was the first publication. People had recognized the shapes as being similar to stromatolites in modern environments and said that this was the oldest evidence for life.
Which are usually found in coastal regions, aren't they?
Exactly. Right. They're best known from coastal regions. In fact, also in Western Australia is a famous place called Shark Bay where big stromatolites are growing, all made by organisms you can't see, but, you know, meter-high structures, big structures that you can swim around. It looks just like a reef, but made up of these living boulders. It's made up by life. But these structures had also been thought to be in a shallow marine environment so very long ago, because we could see ripples in the sediments, we could see places where the sediment had actually dried out and was cracked, all these features of the modern environment. But with more and more research, we started to realize that the environment was much more complicated than first thought. So we have this beautiful exposure, and northwestern Australia is a semi-desert. It's not the drifting dune fields like you have here in Saudi Arabia, but you have this incredibly dry environment with lots of beautifully exposed rocks, but there are grassy bushes and trees on the river courses, these big, long, sandy rivers that only fill up when they get a cyclone coming through. So it's this wonderful, very Australian environment with kangaroos hopping around, and in fact also the occasional camel. Because in the early days, when the gold exploration, they had Afghan cameleers come and use these camel trains to take out the wool and also the ore. So there were wild camels up in northwestern Australia.
Yeah.
It's this wonderful environment. In the winter, it's about 30 degrees. It's very pleasant, no flies. So, it's very similar to here, really, similar kind of conditions. But this area is one of only 2 places in the entire globe that has these very ancient rocks that are very well preserved. It's like walking on the beach, but 3.5 billion years ago, when the sky was orange because it was filled with carbon dioxide, the seas were green because they were filled by iron, there was no oxygen, we couldn't have lived there, we couldn't breathe any oxygen. So a very different planet in deep time. And as we started to recognize this environment and those features that have been pointed out a long time ago, we started to expand our investigations. So from the one area where it had known, we started to map that same unit along strike, and we found huge changes. And over short distance, even from you to me, the rocks would change. And that's very different from an ocean environment, because if you go to the beach extends for like as far as you can see, right? And you get the same kind of environments over tens of kilometers. But here we were finding changes over tens of meters. Because the area had been really faulted and broken up, and there was lots of evidence of hot fluids coming through the system, we knew then that it was actually in a volcanic caldera, the throat of a volcano that had sort of drowned and been wet and then affected by all this jostling around. So not like Shark Bay at all, which is dead still, quiet and flat, but a very active environment. And then I've had a grad student, a PhD student, a young woman called Tara Jokic, and her task was to see what the relationship was of the fluids moving through the crust to the stromatolites at the surface. And she mapped and mapped and mapped, walked around these really rugged hills through the spinifex grass, and she found a sample that we had never seen before. And it was pure curiosity-driven science. It was like, what is that? And I would have walked past it like, 100 times because it's not very interesting, just keep going, to what I knew, right? But because she was new, because she was a really interested, motivated student, she took a sample. And when we brought it back to the lab, it had these textures that were completely novel. We'd never seen anything like it before. And it turns out that the only thing it looked like, as well as not just the shape but the mineralogy, was the deposit from a geyser. We actually had the deposits from splashing hot water on the surface of Earth 3.5 billion years ago. And this was an incredible discovery that was published in Nature Communications, one of the leading scientific journals in the world, and really transformed the way we viewed this environment. Sure, there were traces of this sort of shallow marine, but all the action in terms of life was around where we found these hot springs. And so then once we found one, we started to find a few more, and then other types of rocks that all suddenly started to fit into this picture. And we realized that such an incredibly long time ago, life was flourishing on an exposed land surface in these wet, dry, splashing hot springs that change, because water flows over the surface and gets concentrated and dry over here, and like all this change, all this chemical energy as well. And all of a sudden we realized that from 2 different fields of science, from the theoretical aspect of origin of life, hard in oceans, but better on land, and then in this deep time setting, we found this perfect analog for hot springs. And it was inhabited by microbial life. And it was just like, wow, it really has been transformative. Right. And it's allowed both Tara and myself opportunities to start learning more about chemistry, about fluids, about life, about reactions, and all this prebiotic thing about making polymers. So it's really been a change in our operations, and now expanding, and we're making new connections with researchers who are experts in hot springs in New Zealand. We did a film in Iceland on hot springs, which we're going to show tonight at 7:30 here at KAUST for the first time. And really our science is now penetrating into that field of the origin of life, because this is the only place in deep time where we see a setting that is possibly what the oldest settings would have looked like.
Yeah. And this interest in transdisciplinary science in a way, it seems to have led you into astrobiology quite well. So talk about what astrobiology is, and maybe a bit about where that's going for you and your team.
Yeah, so astrobiology has been, I would say it's probably been one of the first disciplines that really has tried to bridge these academic silos and bring them together, because life, you are physics, your chemistry, your biology, your air, your water, your microbes, you're an organism, you're all these things. And so what astrobiology has done in the challenge to search for ancient signs of life on a different planet, we've had to really get to know life on Earth. And that may sound extraordinarily simple and kind of funny and strange, but like I said, most people associate life with, fish when you go diving and land animals and stuff, but we're talking about microbial life.
Yeah.
And that is unbelievably diverse and complex, and inhabits everywhere from the clouds, through the surface, inside our bodies, down into the crust for up to 4 kilometers without any use of sunlight. There's these chemical factories and engines that microbes can use for making their life. And so we've been learning over the last 15 years that this incredibly diverse array of primitive life, but actually even simple single-celled organisms are unbelievably complicated factories and machines. It's just extraordinary. So we've been learning and enriching our knowledge about that, because if you have a whole planet to go to, like Mars, you go and look at Mars, it's about that color, right? It's red, it's dusty, there's no signs of water, it's just, why would you go there?
Right.
But actually it has a huge diversity of past habitats, of ancient habits when there was water on Mars. And so then you have to think, if I've got one chance to go and search for life on Mars, on a new planet, where would I go?
Is there life on Mars? Is there any signs that we're going to find life? I know that you've been involved in some capacity with the Mars 2020 mission and things. Talk
right.
about that, and where are we in the science in terms of life on planets not Earth, essentially?
So there have been tantalizing hints about the possibility of life on Mars. And there's no direct signs of life on Mars. I'm going to say it right now.
Okay.
There's nothing concrete. There have been false starts and actually, in fact, big announcements about the discovery of life on Mars. But as science has probed further, those have fallen apart. What they have found are some of these organic molecules, but extremely simple. And those can form just in the solar system, or because of the interaction with cosmic, blah, 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 but no direct signs of life. What is exciting about Mars, and what has really been developed over the last 10 or 15 years, is that we know that there are these signs of that it was a habitable planet. It had all the ingredients for life.
Right.
It had water, it had heat from volcanoes, it had an atmosphere, it had running rivers. It was warm and wet in its very distant past. About 3.84 billion years ago, it actually had a hydrological cycle. There were hot springs. We know we've actually found hot spring deposits on Mars. They're bright white, like this table, made out of opaline silica, which comes out of hot springs. And we're really excited because of that idea of, the preservation of life signatures in really ancient rocks on Earth. And this idea of an origin of life in hot springs. Our feeling is that the best place to look for a very simple primitive life would be in hot springs. If it's anywhere on Mars, it should be in hot springs.
So is the contention then that Mars kind of beat us to developing primitive life and never evolved into higher levels of complexity, or what's your thinking?
So I don't know about whether it beat us to life, because as I said, on Earth we don't have a record that goes beyond 3.8.
Right.
But Mars is a real neat snapshot of early processes that probably would have happened on Earth as well. And so one of the interesting things about going to Mars is we can see a history of the solar system that we can't see on Earth anymore. We see the ancient crust, we can analyze its composition, and we can search for signs of primitive life. But the interesting aspect about Mars is that even though it's much smaller than Earth and now is geologically dead, in terms of preserving a window when you might look for, signs of the development of life, that's actually a really good place to go. Yeah. So previously, I wasn't that excited about going to Mars because it didn't have an ocean, and we thought about this model of the origin of life in the deep seas. So if Mars never had an ocean, why would you go, right?
Right.
But we know it did have enough water to make standing bodies of water, flowing rivers, and it had a long enough time that life could have got started there. So, as you mentioned, I've been involved in going to the workshops to decide where to land the Mars 2020 rover for the last 3 years. We've made presentations on supporting the hot spring origin of life kind of hypothesis. But just at the end of last year, so we were in the top 3 landing sites until the last landing site workshop in last year, and then right at the end of last year, they decided on another site, which is where a flowing river comes into a delta or into the crater and makes a delta, and there are lots of sedimentary rocks you can see, which is where we get a lot of life today, and they're interested to search those sediments for preserved molecules as signs of life. And that's the follow the water model. Right. We had a different take where we thought, that would require complex life and concentrated organics and like a thriving biosphere for which there's no evidence yet on Mars. Right. We think that's probably a more sophisticated, longer-term sort of life model. But if it only had a short time to develop, only got a certain distance, we think this sort of chemical life in hot springs is maybe a better chance. So we're actually starting now to think about whether we can develop interest in a new mission to Mars, to look for hot spring samples, to sample hot springs material we know is there.
Very good. I want to see if we have any questions from our audience. Does anybody, anything anybody want to ask? Yeah, please.
Thank you. This is on?
Yeah, we can hear you.
Okay.
Yeah.
Thank you for a very interesting talk. I apologize that this question kind of comes out in fits and starts, so I'm not quite sure how to ask it. But it's basically related to the necessity of an active geology, like active volcanoes, like we have here on Earth. I think you mentioned that in Mars, that whole system shut down at some point in the past. There are big volcanoes on Mars, but they're not active at present. There are no active hot springs. There's no active geology in that sense on Mars. And I wanted to ask if you feel like that kind of an active geology system is a necessary condition for life. I feel like you were dancing around it a bit and talking about focusing on hot springs. Hot springs seem to presuppose an active volcanology or something like that. So I guess that's my question, is do you feel like that active volcanoes, or however you want to phrase it, is a necessary condition for life?
Was that an essential part of the creation of life, essentially?
Yeah, and I think you asked the question very well, and it does get to the nub of one particular problem. And so I want to make it clear that we're not going to Mars to search for recent life, even though there's maybe the possibility if life got started could have survived, but that's a different story. And the reason we're not going to search for recent life is because we're worried about contaminating a possible Martian biosphere with Earth microbes. So we're not interested in early life, we're interested in ancient life. And in that ancient record, there are signs of volcanoes. So Olympus Mons, all those ones you talked about, they were active 3 billion years ago, right back to 4.2 earlier. So that period of the warm and wet Mars was also geologically very active. There would have been a steam atmosphere that was rich probably in sulfur dioxide, carbon dioxide, and other gases that could have been part of this cycle. And so yeah, we think that the early history, that volcanic component, it provides the heat for making reactions and driving water through the crust. And it's that process of driving hot water through the crust that liberates minerals and elements that are required for life. So absolutely, a volcanic component is critical to get life started, but once it's established a foothold in a water body or in some environment, you can take the volcano away, but there's still nutrients in the crust that it can live on. So it's not, the fact that Mars is now dead doesn't mean that there couldn't actually still be life on Mars, okay? So, I mean, that often gets a lot complicated. There's another part to your question, which I didn't talk about, and that's whether you need the particular style of heat distribution on Earth to get life. And currently, like, our planet works with these moving tectonic plates, and it's actually just a result of convecting mantle. So hot magma in the Earth boils up because it's, trying to lose heat to space, and in that process of rising, it then spreads, and the plates, the crust of the Earth moves across. So that's why we get volcanoes and earthquakes. That process also drives chemical complexity and differentiation. You start to segregate materials into the mantle and the core and into the crust. And there is a question about whether you need plate tectonics and a global ocean to drive it to get life. Because some of the components you need for life only come when you sort of differentiate the material of Earth. That we only have limited evidence for on Mars, but we do see areas where you get that differentiation. So really, Mars does have the whole recipe. Not in the same way that Earth does, but it's also a lot older than the record we have on Earth. And maybe that's what early Earth looked like as well. That's where we're getting sort of out of our knowledge zone into a bit more speculation, and we have to rely on modeling. But the fact that we see those components on Mars gives us real hope.
You say that there was a bit of water. Is it believed that there were seas in the same way that there are on Earth, or was there never that amount of water? It was always sort of subterranean. Give us a sense for that.
There's evidence that during the warm and wet period, Mars had significant standing bodies of water.
Wow.
Like on the order of the size of the Black Sea or the Caspian Sea or so, but not a global ocean.
Okay.
And so it didn't have as much volume of water, but it did seem to have water across the entire planet as big river systems. And now, a lot of that water, of course, has been lost to space, because when it loses its atmosphere, the molecules just evaporate and there's radiation that breaks it down. But there's quite a lot of water trapped as ice just below the surface.
Oh.
And it's only in the last year that they have really good images at places where you get the rim of a crater so you can see down across, inside the surface. They've been able to use spectrometers and find reflectance signatures that show there's water ice preserved just beneath the surface. And on some craters, on a summer day, that ice actually starts to melt and makes little tributaries down into the bottom of a crater. And in some craters, they've even shown like a puddle of frozen water ice. And so this idea, if life got started on Mars, now that the volcanoes are dead, there's still enough of a day-night, summer-winter change to allow periods of liquid water. And so maybe, if life got started, there are still habitats where it may still exist. But that is highly speculative, and I personally don't find that so likely, but we don't know unless we go. And so the Mars 2020 mission is exciting because it's planning to take samples and not just analyze them with the scientific instruments on board, but put them on the surface for a later mission to bring them back to Earth, where we can study them with all the sophisticated science technology that we have and really start to find out if there are these very faint chemical traces of life preserved in these rocks. So for that reason, Mars 2020 is really exciting. It's hugely ambitious. They haven't got the technology yet on how to get the samples back from Mars. They can go there and they can get the samples, but they're working like mad now to see what do we need to do to pick up those samples, bring them up to orbit of Mars, and then somehow get them and bring them back to Earth. That's still like a 10-year project. So, by the time those samples come back, it's going to be a long way down the road.
Any other questions? Yeah, please.
Yeah, Martin, thank you. Great, fantastic talk. I wonder a little bit, can you tell me a little bit more about the atmosphere of the Earth when that early life started up? How was that? Could I have breathed it, or what was it like to be on Earth at that time, 3.5 billion years ago?
Yeah, so it's fun, and I'll paint that picture in the talk. But this idea of deep time, and the beauty of geology is that we're actually time travelers. Mm-hmm. So I brought along a friend today, one of my little pieces that I travel around with. So this is a little piece of rock that you would walk past every day on your travels or on your cycles through Saudi Arabia. Mm-hmm. But that rock is 500 million years old.
How do you know that?
Because it contains little crystals, and inside those crystals, it takes up uranium. And uranium's a radioactive element that splits apart naturally on its own.
Oh.
And then it breaks down to another element called lead, and we can measure the ratio of lead to uranium. Mm. We know exactly how long that takes if you get so much lead, so we can date that to plus or minus 1 million year out of 500, like really good precision.
Right.
And so we've done that all around the world. And the beautiful thing is that, my expertise or my business is I go out and look at different rocks, and if we think of rock A and rock B and rock C and rock D, I look for the relationships between them all and see which one is younger. Which rock lies on an older rock, or which one cuts it if it's a magma or a vein or something. And then I choose those samples and I do the dating analysis. And it turns out that one always gives an older age than the one that's cutting through or is younger. It's this science of building up the story. So we're four-dimensional storytellers because we deal with time as well as space. But these samples, they allow us to travel back in time, because if you look very carefully inside that, if I took a slice of that sample, I would find little remnants of life that don't look anything like life today. So I know that life has changed. So I know at 500 million years ago what life looked like at that time.
Right.
But 3.5 billion years ago, there's only faint traces of life. Usually they've been affected by minerals and other things, but there are chemical components of the Earth's atmosphere trapped in bubbles in rocks. And we can analyze those bubbles and get a feeling for what the atmosphere was like. And one of the big revolutions in Earth science is the discovery that about 2.5 billion years ago, there was a dramatic increase in oxygen in the atmosphere. And we know that because oxygen is an incredibly reactive molecule. So if you think about, let's say that this is a cup of coffee with some sugar dissolved in it, or tea with sugar. You don't see the sugar. But if I add something into it, or if I let the water dry out, those crystals will come out and I'll see them. So on the early Earth, there was a lot of iron in the oceans. The oceans would have been green, not blue today, because it's reduced iron, dissolved like sugar in coffee. But as soon as you add oxygen to that iron-rich ocean, the iron combines with the oxygen, and it makes a mineral called hematite, and it drops out. And then makes these bright red rocks, which are deposited all around the world at about 2.5 billion years ago. So we know that oxygen was starting to rise and dropping out the iron from the oceans. But before that, the atmosphere was very rich in carbon dioxide, very rich in nitrogen gas, and rich in sulfur dioxide. And so the fact that I say oxide is not the same as oxygen. Oxygen is a free molecule that's only produced by biology. But it's very common, and it combines with other elements to make these molecules like carbon dioxide or so. So you would not have been able to live on the surface of Earth 3.5 billion years ago, because we need oxygen to live. We're eukaryotes, which is a more complex type of cell that requires oxygen to metabolize. All the earlier simple life can use just the abundant chemicals that we would have found. So on early Earth, the sky would have been orange, the seas green, and the land surfaces would have been these black volcanic rocks, like you see in the Galapagos or Hawaii, because there's no fungus, there's no green canopy, there's no trees or anything, so just these black volcanic land islands in a green ocean with an orange sky. And in the shallow water, on land, life started to get a foothold and change that surface very slowly. The extraordinary thing is that these tiny microbes, once they got a foothold and became successful, they expanded and they used carbon dioxide and water and they made oxygen. So in fact, the 17% of oxygen in the atmosphere now is all because of single-celled microbes. They changed the planet completely and forever, and it allowed us to evolve and to live. It's an amazing story.
Fascinating.
Yeah.
You make this so real, so palpable, and so we're really looking forward to your keynote this evening.
Thank you.
Give us a very quick teaser as to what you're gonna be talking about.
I'm going to talk about everything we've talked about today. You've actually already, spoiler alert, you've already heard the whole thing, but in a more sort of organized way. But I lead the listener, and I've done this now for a long time, and it's a beautiful story.
It really is.
And, putting that together so that people can follow in still a scientific way, but without it being very complicated and talking about specific reactions, that's not necessary. No. The idea of that pathway through time and that our planet has changed tremendously over those eons. So not only did it have an orange sky and green sea, but the way that the planet worked was completely different to the modern day. Mm-hmm. And so, for me, that's what got me fascinated about ancient rocks, because it allows me to travel back to a different planet in my own home. So I'm walking on time every day. And that's the reason that I chose to come here, because of the theme of time. Yeah. It's what I do. And I feel incredibly fortunate to have, 100 million friends called rocks and listen to their stories. Look and listen to their stories.
Captivating. Thank you for being here with us. We really appreciate it.
My great pleasure.
And that's all the time we have for today. Join us at 3 p.m. as we speak with artist Rachel Sussman. Remember to comment, like, and share using hashtag WEP2019. And from everyone here at KAUST, thank you for joining us.